Okay, folks, welcome. Today we have a very exciting guest, John Gustafson. Today's going to be talking about a really fundamental problem in computing. So as many of you know, most of science and engineering has been done with analysis over real numbers, but it turns out computers don't and can't run over real numbers. So there's been a tremendous amount of work in numerical methods trying to deal with that gap. And John's been at the forefront of this for a long time, especially in the context of HPC, where he coined the phrase Gustafson's law.
I didn't coin it. People don't coin their own phrases.
Oh, sorry.
You have to have laws named after you by somebody else.
Where he invented Gustafson's law, and has been in a bunch of different places, including director at Intel Labs. Currently he's at NUS in Singapore, and he's going to tell us about this recent development of posits, which is a sort of radical departure from the hegemony of IEEE 754. So we'll hear more about that today.
Thank you very much. Thanks, Zach. Yeah, and thank you all for coming. It never ceases to amaze me how many people are interested in a subject as inherently dull as computer arithmetic. But here you are all. You're all here. All right. So I think I should give you an outline for what's going to happen. First of all, this was a result that goes back to February 2016. It was announced at Stanford. And the excitement that happened afterwards was nothing like what had happened previously when I put out a book called The End of Error, and it was about a different style of universal number computing. This one is hardware friendly, and at that point, people started getting interested. So the clean slate design of a number system where you're not wedded to existing standards or what you were taught in school, and I'm going to talk about that, and for the first time anywhere, I'm going to talk about the choir. In fact, every single slide you're going to see is new. I just finished most of them within the last several hours. So I hate repeating talks, but I haven't freshened up this material for some time, but I had a mountain of things to talk about that are not anywhere else to be found, not even on our posithub.org's website. I'm going to tell you about a software emulator for posits that's fast enough to be practical right now and how hardware is coming along for doing this stuff. But maybe the meat of the talk is what you can do with posits, because we've been building up example after example where these things are being very successful. Computational fluid dynamics, linear algebra, and an important accuracy technique that applies to a very broad range of calculations. Fast Fourier Transform signal processing, neural networks. This is the hot one. I happened to stumble upon a number system that seems to be like it was tailor-made for doing both inference and machine learning. I really know very little about the topic, but everybody says this is exactly what they've been looking for. And finally, next generation arithmetic, what should happen next? So posits were introduced at a Stanford talk. It's a seminar called EE380, and they put this classroom lecture on the web, on YouTube, in case their students want to refer to it. And usually they get about 300 views of people who are interested in and tap in. This one has 11,000 views and rising so far. As numbers on as lectures in EE380 go, that's going viral. Okay. Near the end, by the way, if you ever want to pull this up and look at it, Dr. Isaac Yonemoto did a live demo of successful machine learning using 8-bit posits, and he did something no one's ever done, I think, with anything less than 16-bit precision before. Yonemoto is quite an interesting guy, by the way. He is a superb mathematician and programmer. Very fast programmer, but he's actually known as a cancer researcher, and he loves to develop cancer drugs that he can open source. So if you Google Isaac Yonemoto, he says that can't be the guy. This guy's, he's dressed in a white lab coat and he's working. That's him, but he's one of the authorities on positive arithmetic as well. Okay, the revolution is underway. This is just some of the people in industry that are at some level exploring positive arithmetic. And you'll see companies you never heard in there, probably, like Posit Research, but also maybe a few things like IBM and Google that you have heard of. And I've given one talk at Google, and they asked if they could send my presentation to 4,000 engineers. I said, sure. And I guess I'm going to be talking to them tomorrow. So they brought me back for a reprise. And then the universities and labs are all working on it, because this is like it's a PhD thesis generator. You pick up almost anything you already know how to do with floats, try it with posits, and you've got yourself a dissertation, and see what happens. So it's very popular. So examples of work on posits, just let me go through some of the ones I think are most important. Micron Technology is working on posit hardware. This really starts with the guy in the headquarters in Boise, Idaho. I just found out that the largest private employer, largest industrial private employer in Singapore is Micron. They got huge fabs there, and that's where they build their flash RAM. So I can satisfy both the countries by working with Micron. If I do anything for DARPA, they'll be happy I'm working with a U.S. company. If I do work for Micron, Singapore will be glad I'm working for something that helps the local industry. Now, Satoshi Matsuoka is a name some of you might know. He's at Tokyo Tech. He's a pioneer in supercomputing, building big supercomputers in novel ways. And he wants future versions of Fujitsu's ARM processor, I think it's the A64FX, to switch to posit arithmetic. He's a big believer. And since he buys millions of dollars of these things, I think they might be listening to him. He's the one who's in charge of designing the Post-K computer, which will be the world's fastest computer probably for a while, and certainly the fastest one in Japan. The National Singapore Supercomputer Center has issued a tender offer for a supercomputer supporting posit arithmetic. And again, you wave millions of dollars in vendors' faces, and suddenly they get really interested in knowing what's this all about. A major cell phone company that I cannot name is testing posits as a possible solution to how do you do 5G. They don't have enough accuracy to do things like FFTs and singular value decompositions and all this stuff that they need for very aggressive signal compression. DARPA has funded a 2-year study of the application of posits to its Transformative Design Program, or TRADES for short. Ruth Ann is actually the head of that and she recruited me for that. A major social network company has a VLSI design team building AI silicon based on low-precision posits. You can tell I'm under NDA for some of these things. And Bosch has designed a scalable Verilog posit generator, so they can generate either FPGAs or VLSI, and they hope to use it to actually increase the efficiency of their FPGA design, which they put in. They do use FPGA in some of their products. So if they can use either a smaller FPGA, it saves them money, or if they can put more processing power on it because these things are more compact, smaller, simpler, that will help. So, clean slate number design, and why number-friendly format isn't hardware-friendly. We've had to learn this the hard way probably since about the early 1900s. Let's go back to the most ancient of all formats, unary. Unary is like tick marks on the wall, and as soon as you get 4 of them, the next one is a scratch. That's the most primitive way of counting, not with numerals. But it started to become numerals, of course, in Chinese and Japanese. Ichi, ni, san, you've got the 3 first numerals. At 4, it kind of breaks down, and they start making a special character for it. Roman numerals, 1, 2, and 3, and then at 4, it breaks down, and you start making a special character for it, IV. So it didn't go very long before they said, wait, this is not going to scale. Hey, maybe if we did like angles, and we put a bunch of lines together, and we could draw them pretty fast, and count angles instead of lines. Well, here's an interesting system somebody came up with a long time ago with a 1 and a 2 and a 3. Interesting. These are where digits came from. And it started out sort of as a unary system, but then it became Hindu-Arabic notation. So regime notation shouldn't be that strange to you. This is what I need. If I go back to, how would you do Roman numerals with negative numbers? Well, if I give you 2 symbols, not just I's, but O's, I say the O's are negative and the I's are positive, now you're getting somewhere. How many of them in a row? But you have to know where to stop. So there's a termination character, which is the opposite. So if you start with zeros, you're going to have a run of some number of them, and then when you finally hit the 1, now you know what number you've got. So they're self-delimiting. And the system needs to be able to represent 0. So it looks a little funny, but 1 followed by 0 means 0. But 0 followed by 1 means -1, which looks a little asymmetric. But when you think about it, there's a lot of things like 2's complement representation on a computer for integers. That's also asymmetric. So we're used to this, if you think about it. So the number it represents is -n if r is 0, if the bit is 0, and it's n-1 if r is 1. Now notice that if you're close to 0, you need very few bits, which is why it's easy to write Roman numerals like 1, 2, and 3. You just very few keystrokes or pencil strokes. But if you have a really big number, clearly you don't want to do things this way. But this is the beginning of tapered accuracy. Numbers that are very big are used less than the very common numbers near 0 and 1. Those you use all the time. So the more common a number is, the less space it takes up. That's tapered accuracy. That's going to be key. So circuits already exist for decoding these things. There's a very common instruction called count leading zeros, CLZ, or in Singapore they always tell me it's CLZ, but it's already part of standard floating point circuits. Now, why does floating point need to count leading zeros? Well, suppose you're doing it a subtraction like that. You take 1.005 minus 1.0003, and you wind up with something that may have leading zeros. In fact, in this case, it did. And so it has to be able to count how many of those, because it's going to scale this to put the 2 back in and say, oh, that's 2 times 10 to the minus 4. So we already have this circuitry in designs. All I'm going to have to do is I'm going to have to apply it to every number before I do the operation. That's about the only thing that I'm doing that's more work than floats, is I immediately decode the regime before, so I can take apart a number. A circuit designer pointed out to me that this might be a great place for mixed analog digital circuits, because he can build something that just instantly in analog counts the voltage of all those zeros in a row or all those ones in a row and turns it into a digit. That's a cute idea. I'll bet that is faster. If you do that, look at the assembler for this instruction. On Intel processors, it takes 3 clock cycles. On AMD processors, it takes 1 clock cycle. I thought that was interesting. Apparently, Intel didn't think it was worth the transistors to spend. But who knows? So positional notation is what we're used to. As opposed to unary notation, we're used to this is the ones place, this is the tens place, this is the hundreds place, and that's how you read numbers, that's how you write numbers. But something a lot of people don't know. Suppose you wanted to note 12 times 12, okay, 144. So the system as it was originally invented says that's 4 ones plus 4 tens plus 100, because you have to start, of course. You know there's going to be ones, but you don't know if there are any tens. Oh, there's some tens. Are we done? No, there's 100. So reading from right to left, I mean left to right, that's how you should write the number. Otherwise, you have to go all the way to the end to find out how big the number. You don't know that the first digit is the hundreds place until you get to the end of the number, right? So every time you read a digit, you're reading backwards, because the Arabs invented this. They read right to left. But if you teach a preschool child how to read digits, they always ask this question: how come it's that way? And we're just so used to it, we don't even think about it. Just like we say $4, but we write $4, right? Okay, so that's 144. That's our positional notation, very compact. Humans parse numbers like this by looking for the white space on either side, which is sort of like ending with the opposite bit. But we're used to computers that record this number, this number, this number, just by it's in this location, and you pack them together. You don't get a delimiter that says where to stop. So generally, computers parse numbers by fixed location, whereas humans look for the white space in between digits. And you could, well, anyway. The early computers used decimal internally in the logic. Think what this means. They wanted decimal so bad that they made the entire logic of the ENIAC 1946 computer base 10, but they were using vacuum tubes that turned on and off. Okay, so it was really binary at the lowest level. 18,000 vacuum tubes, to be exact. Another machine done about 7 years earlier was the Atanasoff-Berry computer, and that used only 300 vacuum tubes and was actually more powerful than the ENIAC at solving systems of linear equations. So this is an example of a mistake of imposing a human taste on hardware design, because if you write a 1 as in binary, you're going to have to use binary coded decimal, which wastes some bits. It takes you 12 bits just to write the number 144, where, of course, in native binary, that would just be a byte, and you could write it with an 8-bit number as an unsigned integer. So histories, yeah, decimal computers. It looks like when you build something to be internally decimal, it takes about 7 times as many transistors as if you did it in binary. So people figured that out. There was a war between decimal computers and binary computers for about a decade, and finally they said, you know, that decimal is not the way to go. It's stupid. We'll let the computer translate to human decimal and into binary, but inside the computer, it better be binary, because otherwise it's just way too wasteful. But there was a second mistake that happened in the earliest computers, and this is the IBM 701. That's to have a separate sign bit for a negative integer. This is the plus or minus, and then this is how big it is, which is how we did it in grade school, right? You wrote a plus or a minus, then you wrote the integers. Well, that imitates the way we write it, but It looks easy to explain, and it looks like it might be easy to build, but you'd be wrong, because you got problems. It's a bad idea. Here's one reason it's a bad idea. Welcome to the joys of -0. Now you have a number that's equal to another number with a different bit pattern. Think of the logic for just testing whether two numbers are equal. Okay. So that caused all kinds of grief, and everyone has figured out, don't do things this way. There's only one place where you'll still see sign magnitude in use, because it's so primitive and so complicated. IEEE standard arithmetic. Floating point arithmetic is sign magnitude, and all the problems of having a separate sign bit are right there. An interesting anecdote about the IBM 701 is that Thomas J. Watson thought there might be a market for maybe 5 of the machines. They went on a tour of their best customers and talked to them about this machine. They got 18 orders for them. So we told a board meeting, we thought there'd be a market for just 5 of these computers, and we sold 18 of them. And that turned into the famous quote, I think there is a worldwide market for electronic computers of only 5. And if you ever hear T.J. Watson quoted for saying that, no, he didn't say that. He was talking about just this one machine. Remember adding signed numbers in school? Here's the rules. To add 2 signed integers, m and m, you first have to see if they're the same sign or different sign. Because if they're the same sign, you add their magnitudes, right? And then you apply the sign to the resulting sum, and you're done. Otherwise, if they have different signs, well, then you're really subtracting. So you take their magnitudes. Oh, which magnitude is bigger? Because that's the one that's going to win. So the bigger one that's the sign of the magnitude that's going to be in the sum. And, OK, you take the bigger one minus the smaller one, and then you apply that one, the sign to the end, or the other way around. I mean, really ugly. And that's exactly what the computer has to do, is to go through a flowchart like that, just when you're adding 2 numbers. Now, modern signed integers are universally 2's complement. 2's complement goes 0 to, until it looks like the left-hand bit's going to flip. And as soon as it flips to a 1, then you come around. So you go up, and then suddenly you're coming from below up to 0 again. And so you see wraparound. And you know you've overflowed because suddenly your positive number turned into a -1, and you didn't expect that to happen. So you get an indication of integer overflow. So it's not as human-friendly, because look what +5 and -5 look like. You look at those bit strings. OK, I see 0 and 5. And what's that thing on the right? A 1, 0, 1, 1. It doesn't look like even if you know binary, it doesn't look like a -5. But the rule is flip all the bits and add 1 in order to change the sign of a number. Ignore any overflow. Mathematically and computationally, this is so much better. Here's the addition algorithm for 2's complement. To add signed integers, m and m, add their bits. You're done. There are no conditional statements. There are no tests. It just all works out. If it's going to wind up negative, it winds up negative. It just all works. There's something very logical about using 2's complement. That's why it's completely dominant now. So the IEEE 754 standard is what I would call low-performance arithmetic, and we're trying to do high-performance computing with it. It's definitely a format designed by a committee over many years. They spent 6 years squabbling over this thing, the sign bit, the exponent bits, the fraction bits, how many of them there would be. Let me give you a very quick rundown of how IEEE arithmetic rules work. The sign bit is 0 means positive, 1 means negative, unless e is 0. And if f is sign 0, or e is 255 and f is anything but 0, in which case it's not a number, nan, which has no sign and might be any of various types of nan. That's just the sign bit. Now the exponent bits, there's lots of different exponent bits. 5, 8, 11, or 15. Why 5, 8, 11, or 15? Don't ask. If it's 8 bits, treat it as an unsigned integer e from 0 to 255. And the scale is e minus 127. Unless e is 0, then it's minus 126. But wait, if e is 255, then if f is 0, it means infinity or minus infinity, depending on the sign bit. But if f is anything other than 0, then it means not a number. And then there's trillions of ways to express nan, none of which have been defined by the standard. So anyway, fraction bits look like they should be simpler. It's an unsigned fixed point number with a binary point right at the left. So it's between 0 and almost 1. But there's things called subnormals. So if the exponent bits are all 0, then the hidden bit is not 1, it's 0. Can you imagine the circuitry that goes into all of this? What a mess. This is why for the longest time, vendors refused to even put floating point in native hardware in their computers. It like tripled the price of the machine, just doing all this stuff. Posit arithmetic is a clean, fresh mathematical design. There are only two exceptions. This is 0. It's all zeros. This is not a real, NAR, not NAN. So call it NAR. And it's just a 1 at the front. Looks sort of like -0, doesn't it? A sign 0. But it means exception value. Or it looks like this. 2's complemented if it's negative, because it is a 2's complement number. And the sign bit is always 0 if it's positive, and it's always 1 if it's negative. That's the rule. The regime, you count it just like the Roman numerals I showed you. And it's like a super exponent, an exponent of an exponent. And it's an integer for scaling. The exponent bits, there's just 2 bits. There's no offset. There's no bias. It's just an integer. So if it says 0, 0, that means 0. 0, 1 means 1. 1, 0 means 2, and so on. Just like you'd say. The number of bits you get for the exponent is the log base 2 of the size of the number minus 3. So this is a 32-bit number. Log base 2 of 32 is 5. Subtract 3, and you get, it should be 2 bits in the exponent. Then there's a fraction bit. There's the hidden bit is always 1. Even if there aren't any fraction bits, like you'll see that this regime, suppose it got really long, because you can have any number of them in a row, right? The regime can actually push the exponent bits off the end of the number, and can push the fraction bits off the end of the number. Doesn't matter. If there are no fraction bits, the hidden bit is still 1. So it's still something times 1, but there's no other significance. You'll see how this works out geometrically. I used to explain this geometrically first. Now I'm presenting this format first, because I find I've tried different ways. A lot of people want to see this right up front, but I'll show you where this comes from. You want to decode this as a human, or you want to decode it with hardware. The way humans understand decoding is first check for 0 and NAR, and if it's not one of those, then record the sign bit. If it's 1, then flip the whole thing 2's complement, so that you're always dealing with the positive side. And then you find the k value from the regime, how many bits in a row there are, the e value, what's in these 2 bits, and just this read as a binary fraction. Then the posit is the sign times this super exponent thing times the usual scaling by exponent, and then 1 plus fraction. That's the value. I can get rid of all those if tests, though, by checking for 0 and NAR cases while decoding S, K, E, and F concurrently. And then this very strange-looking formula does it all at once. Why 1 minus 3s? Well, think about it. If it's 0, that's 1. And if it's 1, it's -2. Well, that means that on this side of things go from, to you. 0 is here, 1 to 2, or -2 up to 1. So they're actually both heading the same direction. But this is a simple way of expressing that. This is way more hardware friendly. You can go straight to this and decode it. Now, some prefer the geometric explanation, and this is how posits were actually invented. I finally figured this out in December of 2016. This is called the projective real. You take the real number line from -infinity to infinity, and you wrap it around until the points at infinity meet. And that's unsigned infinity. Like a light bulb sitting at the top of the circle would project onto the real line what the numbers are. Okay. Now that's the first step to making an infinite line map to a finite state computer. Because you know you only have a finite number of bits, and you can only do a finite number of things with them, so you can't represent the vast infinity of all the reals. You've got to cut it out and make just a sampling somehow. So start by making the circle finite. Big positives wrapped to big negatives. All of a sudden, if you're going up the circle, see will this work? Yes. As you're going up here, you're going up to positive infinity, getting bigger and bigger, and suddenly, boom, surprise, you're now at negative huge numbers, and then they come back down to 0. What does that remind you of? 2's complement. No one's ever mapped the reals to 2's complement integers. That's what needs to be done. That's a start anyway. There's a lot of other things we can fix along the way. Subtle change, instead of infinity, I need a dumping ground for everything that could possibly go wrong. Because it's not just 1 divided by 0. It's also 0 divided by 0, infinity minus infinity, arc sine of 3, square root of -1. Square root of -1 is what kind of number? But it's a number, right? What does IEEE call it? Not a number. It's a number. It's just not a real number. Okay. So we need a NAR, because every time we fall on a NAR, we want to make sure that falls through to the final answer so people don't stumble into an error, and then something happens to the arithmetic, and it's all fine again. And they never find out that they did something terrible along the way. So I decided that NAR should always propagate. If it's the input, it's going to be the output. So you can't take 1 over NAR and get back to 0. Otherwise, I'd have perfect reciprocation, which would be kind of cute. OK, I already told you that. So the way, now we're going to have to insert something in between 1 and the top. We need a number. What number would you pick? It could be anything. Let's start with 2. OK, what if that's not big enough dynamic range? Suppose we need more numbers. Then we have to find a way, not 3, but a way to extend this. Please, not 3. A way to get a variable dynamic range and adjust it. So here's what it looks like. Here's with 2. And the rule is take the number 2 and square. If you had a calculator with an x squared button, hit it 0 times, 1 time, 2 times, 3 times. That's the ES value. How many times did you hit the x squared button? And if you hit it once, you get 4. Hit it twice, you get 16. Hit it again, you'll get 256. So now you're rocketing up to a very large dynamic range. And yet I've only got 3 bits. I'm starting to color code these bits, by the way. I don't know if you noticed, but sign bits are always bright red. Regime bits are always gold, followed by a brown bit if there's a terminating bit. Sometimes the thing that terminates the regime is you ran out of bits. So this says, like, what's a good example here? 001. OK, 001, that's just, OK, the regime bit is just 1. So that's a -1. There's a 0. And there's a 1, because remember, we have to subtract 1 from the positive cases. So the northeast value is called the U seed. It's the seed of a universal number. And you start with U seed equal to, and you do U seed is replaced by U seed squared, and you do that ES times. And that is exactly what leads to that number of exponent bits in the number. So let's pick ES equals 1 of those cases. I'm going to add 1 more bit, so I'm up to 4 bits now. And I could put, here's the rule. If you can squeeze another integer power of 2 between 2, like between 1 and 4, between 2 to the 0th and 2 to the 2nd, there's 2 to the 1st. And we can't do that here, because that's between 4 and infinity. So we multiply by U seed again. You square it. So in a way, you're squaring U seed on this side, and you're square rooting U seed on that side. So it's going geometrical. The way we populate the rest of the circle is, these are the reciprocals of those powers of 2, symmetrically. And these are the negatives of the right-hand side. By the way, you know the trick for negating a number is just flip the bits and add 1. Ignore the first bit. Flip the bits and add 1. In other words, take the 2's complement of everything but the first bit, and you take the reciprocal of the number. Kind of elegant. And one of them revolves the circle this way. The other one revolves the circle this way. Max pause. This is called max pause. Whatever the biggest number you can represent over here on the right is, and the smallest number, that's min pause for short. And so you create a new max pause out of the old max pause by multiplying by U seed, or divide by U seed to get the new min pause. And notice that you've just appended another regime bit. There's the regime bit that got ended. Okay. All the numbers stood in where they were. The numbers stay in place. You just keep inserting numbers between the ones you had in the circle, but none of them change their value. And we're just adding things to the right. We're not adding things to the front, the middle, just to the right, like you would extend a decimal. Fraction bits finally appear when we get up to 5 bits. OK, what do you do between 1 and 2? Well, there's only one thing you can do, and that's 3 halves. Or between 1/2 and 1, in between that's 3/4. By the way, you lose your perfect reciprocation, because these are not perfect reciprocals. 3 halves times 3/4 is 9/8, so it's 12.5% too high to be reciprocal. But it's close, and that's the worst it ever gets. So you get good reciprocal approximations if you use systems for divide where you start with a reciprocal approximation. So if a new intermediate value cannot be an integer power of 2, you use the average. That appended bit is the fraction bit. And so you can start to see black bits appear. The unusual property is then, I'm adding bits to the right, just the right, but I'm getting more accuracy on the east and west parts of the circle. I'm getting more dynamic range at the top and the bottom of the circle. I don't know another number system that does this. It automatically does both directions. So notice also that half of all the posits use only 2 regime bits before it hits the termination bit. So you've got ones that start with 1, 0, and 0, 1, or 1, 0, and 0, 1. And that's all the way from the east quarter and the west quarter, but not the top and the bottom. So if I have a 32-bit posit, I've got the sign, the regime, and 2 exponent bits. That leaves 27 fraction bits. If I had a float as a 32-bit, only 23 fraction bits. So for half the numbers, I've got 4 more bits of accuracy in the fraction right off the bat. So there doesn't have to be a trade-off between dynamic range and accuracy. It's not that simple as moving the line between the blue and the white in the float. I can get both. I can win because I have tapered accuracy. Here's the dynamic range of floats versus posits. I made up an imaginary float. There's no such thing as an 8-bit float in the standard. So we just have to guess if the standards committee met and decided to have a micro float, a quarter-size float, that they might say a float would have exponent size 3, and then it would go from about 0.008 to 20 in magnitude. The posit does a little bit better and more symmetrically, but take a look at the half-precision float. This is now what the Volta processor from NVIDIA really uses to get its AI speed up. Is it uses half-precision IEEE floats, 16-bit, and it has 5 exponent bits and 10 fraction bits. And there's a sign bit, of course. And you can see the dynamic range is actually smaller than it is for posits, yet posits are more accurate at the same time. Now with 32 bits, they're about the same dynamic range. This is just a teeny bit smaller than what it is. For 64 bits, I refuse to go up to this insane dynamic range. That's not what people need. I've been studying the way people use floating point arithmetic for over 35 years. I have never found anybody who needs 600 orders of magnitude in their calculation. So I think we'll keep it down to 300, and I'll have to suffer somehow. Decimal error and decimal accuracy are often not well defined, so I'm going to be careful to define them. Decimal error is the difference between the log base 10 of the computed number and the exact number. So this looks like an absolute error, but you're taking the log of it first, log base 10. Or, by the property of logarithms, you can take their ratio and take the log base 10. This should remind you of the way engineers compute decibels. Okay, very similar. The decimal accuracy is the reciprocal of inaccuracy or error. So take 1 over that, 1 over the decimal error, take the log of that to find out how many digits you got right. So this will actually be measured in how many decimal digits of accuracy were there by taking the log base 10 again. And of course, taking the reciprocal is the same as taking the negative log of the thing that's in the top. So that's how that works out. Underflow to 0 and overflow to infinity is what the IEEE standard says you should do with a number that gets too big. So like, imagine the very biggest number you can represent, now square it. Oh, that overflowed to infinity. Well, when you do that, you've just discarded a whole lot of information. And on a scale of relative accuracy or anything else, you just made an infinite error. I mean, it seems terrible that you bump up against this ceiling, the biggest number you can represent, but that's still better than throwing away all the information. Decimal accuracy, now that I've defined it, I can tell you about what you get with these floats versus posits. I've got about 1 more bit for 8 bits, but by the time you get up to 64 bits, I've got 6 more bits of fraction accuracy, and that's a big advantage. But there's a range where, because it's going after dynamic range, instead, you'll see, show you some pictures later. It's better for small numbers, but it's worse for very large and very small numbers where you don't usually need much precision. And so over these ranges, posits are more accurate than floats, or at least the same accuracy. This is monotone. Just like 2's complement arithmetic, it maps uniformly. If you draw the curve of here's all the integers with 0, then posits make a kind of a sigmoid, and they go up, and they go up to the biggest number like that. So you don't need separate instructions for comparisons. So you use equals, means equals. Less than, greater than, it's just comparing integers. It's exactly the same set of instructions as opposed to a completely different set for floats like you have now. With floats, a nan is defined as not equal to itself. I think it's the very first lesson of Aristotelian logic. It says A is A. Well, not with IEEE. Okay, A is not necessarily A if it's not a number. And 0 is not necessarily the same bit pattern as -0, but it's supposed to be equal. So what a headache. Taper accuracy means more information per bit. I'll show you why in a bit. There's only one exception value, not a real. If you want a whole lot of information about the garbage that you just generated, get a debugger and find out. Do not expect this thing to be constantly on monitoring all the different ways you could go wrong. Most of the error control against doing something wrong is already in your language. If you're writing C and you take the square root of a negative number, you'll get an error message from the language. You don't have to make the hardware do that. Don't burden hardware with things that languages should be doing. Actually, be above that, you should be doing. You should protect your code from doing stupid things. And if you fail at that, the language environment, I think POSIX specifies what like C should do. All languages will protect you from 0 divided by 0 or whatever you did wrong and tell you an error message. But if it falls through to the hardware, all you get is, that's not real. And it goes on, full speed. Only one rounding mode. There are 4 rounding modes in IEEE. Only one of them is ever used. The others, the engineers still have to put in, and it slows things down. Addition is simpler because the 2's complement, just like I said. Addition is not fun in floating point. It takes up pages and pages of code. Multiplication is simpler than floats because floats have to deal with these subnormal numbers that the hidden bit is sometimes 0 and sometimes 1. That makes a mess in circuitry, too. It adds about 30% of the size of an IEEE float circuit to have to deal with the subnormal numbers. There's no overflow or underflow. This is the rule of Donald Knuth. He says, don't throw away all the information. For one thing, you need to know, was it a positive or a negative? At least you know that. That's better than nothing. Sometimes it can rescue your calculation just to know things like that. Perfect reciprocals for all the integer powers of 2. And the sigmoid function, if you're familiar with the sigmoid function that they're used in AI, maybe you don't like sigmoid. There's another one called ReLU that goes like that. It just has to be a nonlinear function. People used sigmoid for a while because it was a nice kind of like fuzzy logic type of shape. You can calculate the sigmoid function in 1 clock cycle with posits. Flip the first bit and shift 2 to the right, you've got a sigmoid function. You can calculate the ReLU in 1 clock function as well. So activation functions are going to be super, super cheap, no matter whether you use the traditional sigmoid or one of the more popular ReLUs. Let me show you a tapered accuracy plot. This is what they look like. I've got the log base 10 on the baseline. So this is take all the positive values and look at the relative accuracy of adjacent points. How accurate is that in terms of, if a number was in between these 2 points, what's the most decimals you could be off by? And it tends to rock up and down because as you get close to 2, you have more accuracy, relative accuracy, when you're close to 1. That's called wobbling accuracy, or unfortunately in a lot of the literature they call it wobbling precision, which is a mistake. Now you could take this curve, and if you're doing an 8-bit posit, you could shift that peak, pink peak over to the left if you wanted. Because what you really want in AI is a whole lot of numbers near 0, typically. You want a lot of precision between like negative 0.2 and plus 0.2. Very easy to do just by dividing or scaling up the problem. So that works very well. So what you find is that in many applications, including AI, if you histogram all the numbers that you used, it makes a lump. And a lump is not really what you get with floats. I'll show you this. It's more clear in the 16-bit. The way floats look is flat, except when they hit the subnormals, and then they kind of coast down to no accuracy at all as they run out of bits. They don't have equivalent over on the right. It's been suggested they have gradual overflow, but no, they just have gradual underflow. Whereas there's a symmetry in posits, and this is the sweet spot where you have more accuracy for the posits. And these seem really well suited to signal processing. 16-bit floats are not enough for signal processing, not quite. And that's why people have to jump to 32, which costs obviously twice as much. If there's one thing that's I/O bound, it's signal processing by the nature of it, right? So if you could get away with 16 posits and do decent, like FFTs, as I'll show later, you just doubled the speed of all the signal processing and image processing being done in the world. Here's what 32-bit looks, and now it's starting to get real smooth. And you just see kind of blocks of all the jitter going up and down because there's so many repeats of that before it changes the exponent. But you see how what a perfect tapering that is. Now, that's with ES equal to 2, which I think is the right size for 32. If I change GS equal 1, I get one more bit of fraction, but it comes in by the whole dynamic range is cut in half. So the triangle gets half as wide. Now, I have a feeling there are some algorithms that at least need more than 10 to the minus 18th to 10 to the 18th. That's probably not enough. So I can come close to matching the dynamic range of 32 bits this way. What about fixed point? I mean, a lot of people are working on fixed point for AI, for neural networks. Here's what fixed point looks like, depending on where you scale it. That's not really what you want. You want more accuracy when the number gets small. This has got more accuracy when the number gets big. It's just the opposite of what you want. So you really have to piece these together with some intelligence as to, well, slide the ramp to the left. No, slide it to the right. And pretty soon you've reinvented block scaling. This is what Nirvana did before they were acquired by Intel. And now they're trying to push for this with a 16-bit fixed point integer and a 5-bit scale factor that you can apply to a block of these things and manage manually. No, don't do that. OK, let's do an example of floating point overflow to infinity. N squared over the square root of n cubed plus 1. Now, just assume n is large. That's going to be pretty close to the square root of n, right? Because you can ignore the plus 1. And you've got n to the 3 halves in the bottom, n squared in the top. Let's call it about n to the 1/2. But try it just with n equals 42 and use 16-bit floats. Now, the exact answer to 3 decimals is 6.47. The posit value is 6.48. Okay, not bad. It's off by a third decimal. What do you think floats do? 0. 0? It's not 0. Well, it is if you overflow to infinity, because n cubed is slightly too big. It's bigger than the biggest number it can represent. It says, oh, make that infinity. And now you take the square root of that plus 1, you get infinity. Take the, So you're dividing by infinity, it says 0. Your answer is 0. Very dangerous. Adding posits. I want to show you how simple this is. You won't appreciate this as much if you have never tried to add 2 floating point numbers in software, actually taking apart the pieces and doing it yourself. Add negative 3.125 to 0.03125, let's say. Here they are as posits. And I've color-coded these posits so you can see the bits. And I'm going to turn those into signed fixed point numbers. Now, you need more bits, of course. But this is first one. That's what negative 3.125 looks like as a fixed point number. Leading ones meaning it's negative. Now, you see this 0, 1, 1 up here? It just got kind of shifted over here. And that's all that happens is the fraction bits just get shifted into place. The shift determined by these red, by the regime and the blue bit. And it's easier to see where this one came from. It's just shifting a 1 over here. How do you add all the different cases? Well, you just add them as fixed point. That's it. I mean, that's like a huge reduction in the complexity of the add on a real type number. And you convert that back to a posit. And the posit, that's again needing count leading zeros. I could do this stuff really fast in C, but there's no way to do count leading zeros fast in C except to write a while loop. If I had that as an instruction, the way I have ors and ands and things like that, I could really do a slick posit add, but it'd have to be left to hardware. And that's the correct answer. So the sign of the result is automatically handled like for addition. There are no conditional branches. If you're a chip designer, no muxes. It's just straight in and straight out. You can imagine real addition can be almost as fast as integer addition with posit format, and yet having this big dynamic range.
In which case, to do the 16-bit addition?
They're there at 56. They're all there. The dynamic range is 2 to the minus 28th to 2 to the positive 28th. Now, it gets a little impractical if you get it into a 32-bit number, and I think then you start want to doing shortcuts. But there are known ways of doing that. Good question. So keep it simple, stupid. KISS principle. I looked at the IEEE standard for floating point arithmetic. The 2008 version runs 70 pages long. We've written up the standard for positive arithmetic. We've got a sketch of it, and it's 8 pages. It might grow to as much as 10. But most of it is just, it's like defining integer arithmetic. You don't think about the IEEE standard for integer arithmetic, right? Now, one of the things we're doing is I define the scientific functions like cosine, log, and so on. They have to be rounded correctly for every input if you're going to call it a cosine. Otherwise, you're using a fast auxiliary exponent, let's say, or fast auxiliary cosine, faux cosine, F-A-U-X, okay? And that is allowed to be off by 1 bit in the last place. And those can be really fast. But I will specify an algorithm that always gives everybody the same answer bitwise, and it will be part of the standard. Here's how you compute the fake cosine. And that way, people will still get repeatable answers between machines and over time. The quire, and this derives from a word for 4 sheets of paper or parchment folded to form 8 leaves. It's just a small book. It's not as big as a file or a book. It's a little subset. If you look at the way books are sewn in signatures, each one of those is a quire. So this is a set of, it's a fixed point number that's going to hold exact dot products. That's part and parcel of positive arithmetic. I haven't had a chance to explain it in public before, but I'm going to try to do that now. So it's a big fixed 0.2's complement number, although it does have an exception value. 1 followed by all zeros means nar, because I have to be able to record that if that's an input. The quire sizes are not too bad. It's half the number, n bits squared. If you have like an 8-bit posit, 32-bit quire suffices to store exact dot product with no rounding, up to some length dot product. Now, it's like 127 for 8 bits. For 16 bits, I think it's 32K. For a 32-bit number, if you have a 512-bit quire, you can store, at the worst case, a billion long vector without any possibility of overflow. It can't happen. That's not very many bits to spend. And notice that 512 bits is, well, I think, oops, did I say that? No, I didn't say it. 512 bits is a kind of a standard size in modern processors because that's the cache line size. And it's also there's an instruction set for doing SIMD instructions called SSE. It's 512 bits wide. And right now they use it for parcels of 64-bit or parcels of 32-bit. I want it just to be an accumulator. And so I think the architecture exists for doing this very cheaply. When they've tried to do this with IEEE floats, there's a problem with the huge dynamic ranges of IEEE floats. They force you to use like over 4,000 bits to store an exact dot product, so it's not practical. But this is practical. 512 bits is quite reasonable. People say, well, we got fused multiply add. We do a multiply and add and then don't round. I can tell that I'm running out of time, so I need to probably shape some of these slides down. But I did want to show what's dangerous about just relying on multiply add being fused. If suppose you just want to take the square root of x squared minus y squared using IEEE floats, write it out, square root of x times x minus y times y, and it so happens that x equals y. Well, you better get 0, right? About half the time, about 8 million times with single precision, of all the cases, you'll get not a number. What? Okay. It's because covertly, the compiler is trying to help you. It first calculates x squared and rounds, and half the time it rounds down. Half the time it rounds up. Or a very small fraction of the time it actually lands on an exact number. Now, if you take that minus y times y, this is fused and it's computed exactly. But you rounded this one down, so this is now a negative number. And now you're taking a square root of a negative number. And that's why you get, you couldn't even compute the square root of 0 correctly. All right. SoftPosit and hardware for posits. It's sort of like the early days of floating point arithmetic, where we had to do things in software, when computers didn't have hardware built in. And I'm delighted to have the help of Sir Liang Xiu-hun. Dr. Liang has coded up a perfect equivalent for the SoftFloat program that is done at Berkeley as part of the Aspire program. He's been tuning this thing for 22 years. So it's really very fast, and the software engineering is superb. But now I can take a code. She took every single routine and coded the equivalent. So you now have a perfect apples-to-apples comparison in software. And surprise, they're pretty fast. A lot faster than I thought they'd be. So fast that they're getting comparable to hardware. Yep, I know, I'm looking at the time too. Okay, so here's the speeds compared. Green is floats and magenta is posits. In fact, that's kind of true throughout this talk. Color coding for posits versus floats. They don't have a exact dot product, but I put it in here. Note that it's really faster than floating point multiply add because you don't round. And not having to round and convert something back into a posit really saves a lot of time. We exhaustively tested the ones for 8 and 16 bits, so these are really solid. For 32 bits times 32 bits, that's too many to test, but we have done very extensive testing. There are wrappers for Python and C++, so you can make these things look just like plus minus times divide like you would write code. Make it totally invisible. The Python one's pretty fun. So you can use it as an interactive calculator for working with posits. And it does include the quire operations, square root, and conversion between all the types. Now, math libraries are still in progress, so don't expect to find an e to the x in there yet. I'm working on it. I'm going to have to do this for all the different sizes, so there's a lot of man work. This is just labor intensive. I need some help. And it's very well tuned. Once you bring in the operand, it stays in register. Everything is register to register, ors, ands, shifts, things like that. So, man, modern Intel processors can just blast through a lot of code if you don't ever touch memory or cache. Anyway, so let me give you some examples of what posits can do. Try them. You'll like them, because I have yet to see these things fail. Here's an independent test by Lawrence Livermore National Lab of a shock wave. Comes in from the left, goes around a sharp corner, And that's usually where you get singularities and nasty numerical behavior. And they measure the root mean square error that they get. So they've got a pretty good typical differential equation solver here. And I actually have, I think I can play this. You'll see what it does as it goes around. And see, the blue is negative pressure, and the orange is positive pressure zones. As it goes through there, all kinds of nasty things numerically happen as it hits that corner. Look at all that splashing and turbulence. Okay, so error comparison for shock simulator. They have a kind of a harness. They can put different number types and solve the same problem. So they tried IEEE floats, and dark is bad. Dark is error. I think blue is negative error, and orange is positive error. And then they tried reducing the size of the exponent and calculating with a larger fraction. It didn't help that much. They tried some things they thought of for doing tapered precision, and they tried posits. And the errors went down by a factor of 50. Now, that's interesting because I only have 4 more bits. That's only a factor of 16. Why is it down by a factor of 50? There's an amplification of error that happens, so I'm getting kind of an error of error of error. That's one reason. And the other is that posits, if you take an operation of 2 posits, it frequently lands on another posit exactly and doesn't have to be rounded. And so for a lot of the time, it's an exact calculation like an integer would be. Here's root mean square error is the vertical scale. And here the time step is it goes through the simulation. Of course, the error tends to go up and up and up. If it ever goes back down, I think they're doing something wrong, because error should never go down. Once you've acquired an error in a simulation, it stays that way. But you can see the best format tested was these guys. That's posits, 32-bit posits with ES equal 2 or 1. The worst number format tested was IEEE floats. If anything, they tried. So everything you do to these things improves them. Okay, they also tried comparing down here the 64-bit formats. That's kind of their gold standard, because they were using IEEE floats. They tried 64-bit posits and got 2 orders of magnitude more accuracy. Again, that's a lot more than the length of the fraction would suggest, so some nice magic is going on here. Recently, I tried inverting a Hilbert matrix. Now, I can invert all kinds of linear equations, but here's the killer matrix to invert. As anyone's ever tried this, this thing is so close to singular. The condition number of just this small one is about 500,000. I get up to like a 12th order Hilbert matrix, and it's 1.4 times 10 to the 12th is the condition number. So this is an extremely eccentric transformation that no one, none of the faint of heart should attempt, especially not with IEEE floats. Now, to make the problem fair, I can't express 1/7 exactly in any floating point number sum or in the positive sum. So I'll scale the whole thing by 315, and now the whole thing is exactly expressible as an input. I scale the right-hand side by the same amount, so I get the same answer. Take AX equals B, just scale X. I scale A and scale B, I'll still get the same X. So let's try that with 32-bit IEEE floats and then 32-bit posits. I'll use LDL decomposition to do the factorization. The float result, I'll take what's the biggest mistake you made, because that's usually what kills your calculation, is the worst one. And the worst case accuracy is 3.7 decimals correct. The worst case posit accuracy is 6.3 decimals. That's 400 times as accurate. And so you're seeing this over and over again. It's only 27 bits of fraction versus 23 bits, but it gets a bigger advantage for compound reasons. But remember, I've got this exact dot product. So what you do is now try it out and see, take that H inverse times H and check it against the inverse matrix and see how close did I get. That can be done exactly, because that's a bunch of dot products. I can subtract my error, and then I can use that as a defect correction. That's the secret weapon of posits, is the quire. And if I do that with one pass, it landed on every integer. The answer is all exact integers. Infinite accuracy. There isn't any error. And this happens almost every time, even when the condition number is huge. So floats can't do that even with double precision. I think they can't even do it with quad precision, actually. They're just inherently unstable. They don't have a lifeline to exact arithmetic. The quire is the lifeline to being able to check anything as exact arithmetic. And I'm glad I've got 5 minutes left. I was hoping to have a lot more time. But the most important thing I'm going to tell you is the next 2 slides. This is an astonishing technique for maximum accuracy. Any basic block of operations involving plus, minus, times, divide, you can write it as a lower triangular matrix times an unknown equals the right-hand side. Like if you have A plus B times C minus D over E, Well, x1 you set to a, x2 is x1 plus b, and then take that times, okay? So I can write these equations one at a time, and I can create 6 temporary values of x. The one you want is the x6. If you can find that exactly, then you can find this entire thing as if it was all fused, if there was no rounding. Well, it turns into a matrix problem, sparse matrix problem that's all lower triangular. I just showed you I can solve a Hilbert matrix, right? I can solve that to within 1/2 of the unit in the last place every time, which means I can guarantee basic blocks in any code can be accurately computed. Now, the Herbie project tries to help people with their floating point error, but with a tool this powerful, maybe you don't need Herbie. Sorry. Think about it. The Quire allows what's called Karlsruhe accurate arithmetic, KAA, and it removes most of the need for 64-bit format. It was invented by this man, Ulrich Kulisch, at the University of Karlsruhe, and this book on the right is one of many he's written, and it's the most recent one, which means it's the best summary of everything he's ever done. Really great for polynomials. If you've got a tough-to-evaluate polynomial, it's like right near a root, very, very unstable, nails it. And it can be done automatically by a compiler. They call them XSC languages, extensions for scientific computing. And they tried to sell these as ways to get 15 decimals accurate every time. And they never thought, well, why don't you just use them on single precision and let people get the bandwidth savings and the memory savings? They never tried that. And so they didn't market it very well. They also tried to charge a lot of money for it. There's nothing that kills a new number format faster than trying to find people for using it. So this is all open source. Everything I do is given away. This is all free, folks. I protect it with the MIT open source license, which I think is one of the most liberal. And now the idea is, if you say, I don't really care about these variables, they're just going to a graphics display, but I really care about this part of my calculation, you should be able to mark that and say what it is. 32-bit posit answers can be more accurate than 64-bit float answers. Let me jump to the Fourier transform. Okay, there's an example of a decimation in, is that time or frequency? I can remember which is which. Anyway, it's very communication bound. Those blue lines take all the time. In fact, if you look at the total length of all the blue lines, it's not order n log n. It's order n squared. So it doesn't matter that your operations are a really low op count. And that's what FFTW, the fastest Fourier transform in the West, developed at MIT, tries to get down. They're focusing on the wrong thing. The only way you're going to make this faster is to make the blue lines have less data so they can move in less time. So it's a much more potent approach to reduce the data size by using the posit format. So I took FFTs with, let's suppose they come out of an A to D converter. And I'm going to take them from the A to D converter, let's say it's a 12-bit A to D converter, and use a 16-bit posit or a 16-bit float. So first convert the number. And then I'll take a forward FFT. And I'll take the inverse FFT. Now I can compare it with what I started with, bit for bit. I can see how many of the numbers changed. And if none of the numbers changed, then I've got a perfect FFT, right? It's absolutely the same numbers. So if you can do that without loss, there's no point in using more precision than that. 16-bit posits can do this, and 16-bit floats cannot. And that's just why they don't use 16-bit floats for signal processing. And you can't do it with fixed point either. So posits are better than fixed or floating point at this. These are the errors. It's a little hard to read the scale, but it can be off by as much as plus or minus 6 if you do floats. And 70% of them are wrong. If you do it with posits, you just get a very few. 98% of them are exactly right. And any errors, there's only 63 of them that are wrong out of the 1,024, or actually 2048 values. Orange is real error, and blue is imaginary error. So that's why the color coding. That's probably enough that you'd do it. You wouldn't worry about it. But it gets better because if you get down to 11-bit A to D converters, it doesn't lose a thing. It's perfect. And for anything smaller than that. So we think that the molecular dynamics code known as GROMACS, which does FFTs followed by computation, it's 64-bit right now. We can turn it into 32-bit. How many of you have a hard stop right now at 3? OK. I'm almost at the summary. I think I have about 10 more slides. I'm going to try to go real fast. And if we don't have time for questions, I'll certainly take them out afterwards. Neural networks have a histogram of, this is an example from Rochester Institute of Technology of what AlexNet uses. And you see a bunch of small values that are concentrated. You definitely don't want just a flat number system. You want it to concentrate its values at small. And with 8-bit posits, we were able to get 67 right and keep on going down all the way to 6-bit. I happen to know that a social network company is getting down to 5 bits. And this is without even using the Quire. We tried using the Quire recently on the MNIST benchmark, And an 8-bit posit got the same accuracy as the 32-bit float, exactly. 99.11% correct. So we got to create the entire stack in order to do this. Rex Computing has added 32-bit posits to their Neo processor design, but you know, I can get this fantastic performance, especially performance per watt is way off the chart, but there's no software stack to go with that. So I need something like ARM or RISC-V, which has compilers and tools. And Indian Institute of Technology in Madras is working on this, and some other places are working on it. Micron's working on it. And the RISC-V extensions for posits are defined, and they're up on the web. So the idea is maybe take 8 of the 64-bit registers and say, use this as the quire. So you don't have to build more transistors for the quire. Just use the registers you've got, section off 8 of them, or use the SSE and say, use this as the quire. It's not going to add a whole bunch of space to start supporting exact dot products, and look what you can do with them. You can make Herbie obsolete. Well, okay. Anyway, so I think switching is going to take about 10 years. It always does. So I see you put your processor into either posit mode or float mode, and you check to see that they both work, and then you use posits because you like the answers better. And then at some point you say, okay, this supports native posits, and we support floats in software. Then we're done. Okay, then we won. This is very similar to what was done with ASCII changing to Unicode. A number of revolutions. It takes about 10 years. Yeah, maybe that's true, and everybody's connectors will stop working. But so I've noticed this is not like parallel processing. I worked very hard to convince people that parallel processing worked, and it was an uphill battle all the way. This feels like a downhill battle. It feels like I've got a tiger by the tail. People can't wait to get the, give me the math library. I want to do it. I want it. I want it now. So in summary, better answers, fewer bits. AI needs have freed people to think about novel arithmetic. Thank you. It was just fortuitous that everybody's experimenting with new number systems now. Posits can fix a whole lot of float shortcomings. And not, all these things have been wrong for 35 years in the standard. We can now fix them. And if we fix them for AI, we also fix them for high-performance computing. Taper the precision, more information per bit. Fit the shape to what the histogram is. Simplify the exceptions surrounding the unused feature. Match the dynamic range to the application needs. Make the exact dot product practical so we can start using it in all of our algorithms. Restores the associative and distributive laws. That's what the exact dot product does for you. You don't have to worry about rounding error if you're within pluses and times. And you get bitwise reproducible calculations so you don't tear your hair out wondering why you're getting different answers now. SoftPosit is available, and there's no reason you can't start putting code now as long as you make it look like C, C++, or Python. It's ready to go. In fact, I would think a Fortran wrapper wouldn't be hard to do if any grad student could do that in a couple of days.
Or Racket.
Or Racket, okay. So as soon as you switch, you get at least twice the speed. What happens when you make the total space taken by your problem smaller? Sometimes it was spilling into level 3 cache. Now it doesn't spill. Now it stays in level 2 cache. Or maybe it stays in level 1 cache. You get a superlinear speed up, not just double. Less energy and power consumption, less memory consumption, less bandwidth consumption, higher accuracy, especially if you use the quire, but you could just do a drop-in replacement and forget about the quire stuff. If all you do is flip to the better representation, everything gets better. It's less chip area per arithmetic unit and higher programmer productivity. Thank you very much. Okay, I got to take 15 minutes out of this talk next time I give it.
Okay, are there any questions for John about posits or the future of number systems?
Back row, yes.
Also, one of the few applications I ever understood for the IPM rounding nodes was to do interval arithmetic, to try and get bounded absolute error bounds and stuff.
Right.
Obviously, you're not going there, and it's not used very much, so it probably doesn't matter. But
actually, I didn't want to go into it, but there's an for all of my arithmetics, I have an interval version and I have a rounded version. The interval version is called valids. So I have posits and I have valids. Valids are much better than interval arithmetic, but they solve the problem of they do the rounding exactly as you described. And it would be very easy to build hardware for doing valids as well. But that gives you both open and closed and half-open intervals, which you need that information to do proper interval arithmetic. And I could go into that, but it would be another 2-hour lecture. But
what are the costs in terms of speed, hardware complexity, stuff like that, to actually implement that stuff?
Well, what you would probably do for fast interval arithmetic is if you have a multiplier and an adder, let's say, use one on the left endpoint and one on the right endpoint at all times. Or if you do a multiply, I guess you actually might need 4 cases to do. But you can actually make it do full speed. Most of the time, all these parallel multiplier adders you've got in your processors, they're just sitting there idle. Like, you know, the passenger seats in an SUV when you commute to work. It's just stupid. They just sit there, empty. But why not use them for doing the bounds on interval? And I think we'll make better use of the equipment that's already put in the chip. But I don't think anyone's done that yet. It's just all those multiplier adders are mainly designed to boost your benchmark score on LinPack.
So posits still have, you know, you can overflow to not a real. You can still have catastrophic cancellation.
No, you can't overflow to not a real.
You wrap around?
No, you stay at max pause or negative max pause. Right. So you still preserve which side were you on when you overflowed, either whether it's too small or too large. Right. You saturate. So one of the things I put into the RISC-V standard, I think this is going to be cheap in hardware, is you can examine what's the largest number I used and what's the smallest number I used in my calculation. And so you take a look at that afterwards and say, oh my God, I threw a gutter ball. I mean, I rolled way over there where I don't have any accuracy. I better find some way to scale the problem back down so it doesn't do that. But if you look at all traditional numerical methods, they try not to overflow and they try not to underflow by keeping the magnitudes near 1. So you probably don't have to do anything because it's already been done for you. All the best algorithms try to keep the numerical ranges from going too far off to the smaller to the very large, just because they're afraid of overflow and underflow. It's catastrophic for floats, as I showed you.
So is it really saturated? If I subtract 10 from max pause, what happens?
Well, it depends on the one. If you subtract 10 and they're spaced very far apart, which they will be, then it will stay at max pause. You probably have to subtract like half of max pause to bump it down to the next one. And that's going to be a half of a very big number. So yes, it tends to get stuck there, which is one thing I like. Max pause is not twice as big as the next one. It's useed times as big. So if like for a 64-bit posit, it's 256 times larger than the next larger value. They really spread out fast. So once you land on that, it tends to get stuck almost as if it was a NAR or a NAN, which is good. You want it to. You want to know at the end, I got stuck. Yes?
So right now in your standard, is the number of fractional bits set in advance, or is there a consensus on how many bits we should use for the fractional components?
Yeah. Remember the regime grows and shrinks. It can be as small as 2 bits, a 0, 1, or a 1, 0. It terminates. Or it can be the entire length of the number, crowding out the fraction bits. So the fraction bits are there. You've got lots of fraction bits if you're close to 2 to the 0th, let's say, close to 1 in magnitude. But it can be no fraction bits. The standard does fix the number of exponent bits that go with each n bit size, even though a lot of these others are quite useful. And for AI, I think people are experimenting with all the combinations. Mathematically, they all work. You have to have at least 2 for the total number of bits, but the ES value can be any integer that's not negative. So you could actually have a 10-bit, you could have ES equals 10 and have only 2 bits, believe it or not. It still works mathematically. You get a huge dynamic range from 3 bits. Wow. But it's a silly number system, but maybe somebody will find a use for that.
So the parameters that set the different positive number systems to use, are those parameters that you found you want to set on a per application level, on a per set of instructions level for each value independently, or something that should be set by the processor designer ahead of time?
I've asked processor designers, and most of them tell me it's very expensive to adjust the ES size at runtime. That it's really going to be a lot more hardware, and that defeats the part of the purpose. So I really believe you're going to want to fix it. In fact, you may discover that you don't even want 16, 32, 64. You just want one size of posit, because the quire gives you so much more amplification. I suspect that may be true. But when I announced these over a year ago, I waited for everybody to kind of debate and juggle this around and tell me what they thought of the different ES values. And I finally arrived at the symbol of 8 has an ES of 0, 1, 2, 3. You just count ES up 1 every time you double the size of the number, starting with 8. And it works out to be very close to IEEE, but not make the mistake of a really silly, huge dynamic range for double precision that no one ever needs or uses, and that makes the quire extremely difficult to build. So I think this is the right decision, but I'd be very happy if I'm proved wrong, and it turns out that we should always use ES equals 3 on all sizes of numbers, something like that. It could be. Yeah?
So one of the most interesting ideas, I think, for posits is this concept of the quire and having completely accurate operations for multiply adds.
That you can check.
Have you looked at, I know you had mentioned looking briefly into doing quires for things like floats, but have you looked into quires for other operations, both so that those other number systems, both so that those other number systems can benefit from this idea, but also to show people that, hey, quires are really cool, come check out posits.
So yeah, the exact dot product has been around since the 1980s. It came out around the same time that the 8087 coprocessor was around, and it failed to beat out the 80-bit part of the 8087 coprocessor, which provided you a little bit of extra protection, was very cheap to do. And so the guy in charge of IEEE really argued it down and said, don't use quires. And he managed to convince the IEEE committee to reject every application there has been to support the quire. Now, when you say other number systems could use the quire, you mean integers? I guess fixed point could do it.
Yeah, so I'm thinking more like fixed point or like soft floats or like the big float, arbitrary precision.
Well, if they start doing a soft float, it's going to be very slow and more expensive and probably messed up by all the rounding modes and who knows what else. But I've tried to make it economical enough and small enough that it still does the job of that exact dot product should do without, I mean, it's over 4,000 bits long for floating point. And you don't casually throw 4,000 bits around. It's just too big. But we do casually throw 512 bits around. We do it every time we load a cache line. So that people shouldn't complain too much about having to do that. No, I hadn't thought about adding quires to other things. In fact, I'm hoping that the only thing supporting the quire is posits. And you have to go there if that's what you want. That would be good, better marketing, I think. Yeah.
So it looks like you start from 8 bits and go up. What if we want to go down?
Oh, yeah. And we did go down for the neural network example. And we tried to go down as far as possible. I hope, I mean, the holy grail is to get down to 4 bits, because that's a nice power of 2, and use the quire for 4 bits to support accurate inference. I mean, people have done inference down to 1 bit, right? So I should be able to get down to 4 bits and use the quire accumulator to get correct inference. But my graduate student has not yet finished those tests, but maybe by the time I get back, she will have got some interesting results. Nothing to stop other people from working on it. There must be a dozen places working on neural network or AI applications using posits, because they're just exactly what you want. They focus a lot of numbers in your 0 and focus a lot of numbers in your plus and minus 1. Just exactly what you need.
Any more questions for John? All right, let's
Thanks a lot.
thank him again.